Third video with Venn diagram and mutually exclusive and conditional probability. We have a group of 25 students. 15 like chocolate milk, who doesn't? 17 like iced coffee, again, who doesn't? 2 students like neither, I guess that's who doesn't, and 9 students like both. 1 student is randomly selected. What is the probability that the student likes chocolate milk given that he or she likes iced coffee? So we're going to start with a Venn diagram. So let's get our circles down. Boom. Boom. We've got milk lovers and coffee lovers, and then outside we've got this universal set including all of the people that don't like both. 2 students like neither, so 2's out there. 9 students like both, 9's right there. 15 like chocolate milk, but there are already 9 in there. That means 6 go there. 17 like iced coffee, but there's already 9 inside the coffee circle. We need 8 right there, and that should total 25 if we add them all up. What is the probability that somebody likes chocolate milk? Okay, likes chocolate milk. Probability M. Well, it's going to be 15 out of 25. Better known as 3/5. What is the probability that they like chocolate milk given that they like coffee? So here, this is one of these where we don't care about the people that are not in the coffee circle. We know that they like coffee. They have to be in this circle. If they're not in that circle, we don't care at this problem. So how many people are in that coffee circle? In that coffee circle, there is a total of 17. And of those 17, how many like chocolate milk? 9. There's our probability. This is a conditional probability. We're putting a condition on the situation saying that they have to like iced coffee. And what we have here, what we just found, is that the probability of A given B is the probability of A intersect B divided by probability of B. Let's look at that. Probability of M intersect C. That's going to be 9 out of 25. Over. Said to divide by the probability of B. So divide by the probability of the condition. That's 17 out of 25. And this does equal 9 out of 17. So let's prove this. We have a Venn diagram with A and B. Probability of A given B. Okay, so probability of A given B. How many things are in circle B? There's B plus C. How many things are in A given that B occurred? So within the B circle, how many of those are in circle A also? B of them. Now, time for some algebraic manipulation. I'm going to divide by A plus B plus C plus D. And as long as I do that to both parts, both the top and the bottom of a fraction, that's algebraically okay, remember. And A plus B plus C plus D can't equal 0. Important thing to note. Now, what is this top really? Well, that's the probability of A intersect B. The number in the intersection divided by the total amount of stuff there is. B plus C divided by that amount. That's the probability of B. So we've just proven that this conditional statement probability equivalence is true. And what that leads us to is some rearrangements of this. The probability of A intersect B is equal to the probability of A given B times the probability of B, or probability of B given A times the probability of A. One thing to note, and this is something that I've observed over time, is that whatever the condition is, that's what we're multiplying by. If it's A given B, multiplying by probability of B. If it's B given A times probability of A, we could go through a similar proof like this for the second one right here. And let's do an example. We have a jar, pink and green tickets in jar A. We have a jar B, same story. We have a die with 5 faces marked A and 1 face marked B, and we're going to roll it to select our jar. Then we're going to pick a ticket from that jar, find the probability that the ticket is pink. Oh boy. I'm going to start with a tree diagram here. Tree diagrams are pretty useful, especially with conditional probability. Any of you that are interested in computing, artificial intelligence, machine choice, that sort of thing, these tree diagrams as conditional probability is very prevalent in that study. So we have jar A, we have jar B, and we have pink and green within each of them. So probability of getting jar A. Well, jar A, 5 faces marked A. 1 face marked B. And once we're in jar A, how many tickets are pink? 2 out of 7. 5 out of 7 are green. Once we're in jar B, 4 out of 7 are pink, 3 out of 7 are green. And now we can find the probability that a ticket is pink. Pink ticket, pink ticket. There's 2 ways to get that. We could go down that branch, or we could go down that branch. So notice I said or. That should be saying, let's add. Hey, let's add. So 5/6 times 2/7. That's the probability that we get a pink one from jar A, plus 1/6 times 4/7. So we have 10 over 42 plus 4 over 42. That's 14 over 42, which is 2/7. Part A, done. Part B says the ticket was chosen from B given that it was pink. So we know that it's pink. What's the probability that it was chosen from B? We know that it's pink. What is the probability it's chosen from B? So we know it's pink. We know it's pink. So what's the probability of it being pink? Or let's start with the probability statement. Probability, let me change colors. Given that it's pink. Okay, so we know that the outcome is pink. So that means, who cares about that branch? Who cares about that branch? I don't. So our conditional probability says that we have to divide by 2/7. We have to divide by 2/7. What is the probability that it's pink? That's our condition. Now, on the top goes the probability of, back up here, this would be probability of pink. The probability that it's jar B and pink. So this is going to be 1/6 times 4/7. That's this branch right here. That's the one that gets us blue, jar B, and pink. We're dividing by probability of pink, which is 2/7. And what we end up with is 1/2. If we know that this ticket was pink, there's a 1/2 shot that it came from jar B.